This lecture is on normal distribution, which is a continuous distribution unlike the binomial distribution. To start with, we have an example on uniform probability distributions. So suppose the United Parcel Service is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 a.m. and 11 a.m. Let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place, and the delivery could be at 10 a.m. or at 11 a.m. In other words, x is equal to 0 right here, is 10 a.m. and x equals 60 is 11 a.m. And the times are equally likely in the sense that the probability that they would drop off the package at 10:15 is the same as 10:16, and it is the same that it would arrive between 10:40 and 10:41. So x can take any value of time between 0 and 60. So and again, 0 would correspond to 10 a.m. and 60 would correspond to 11 a.m. So if we have a density of this sort, we call it a uniform density. You may look at that rectangle and say, why do I see a rectangle? It's not just the rectangle that we are interested in, it is that curve. So that function there is y equals 60, which is a horizontal line. So for a uniform, y equals 1 over 60. For a uniform distribution, the density function is just a line, a horizontal line that is defined between 2 points. In our case, it is between 0 and 60. Before we move further, there is a formal definition of a probability density function. It is any equation used to compute probabilities of a continuous random variable. And it has important properties just like a discrete distribution. In a discrete distribution, such as binomial, if we add all probabilities, it should equal to 1. So let me summarize that: discrete and continuous. So as an example, let's say x would take on the value 1, 2, and 3, and the probability of x is 1 over 3, 1 over 3, and 1 over 3. So here we have discrete values of x, which are 1, 2, and 3. And if we sum all the corresponding probabilities, it would sum to 1. In our example, the parcel service example, the value of x was continuous between 0 all the way up to 60. In this sense, it could be 1.5, 2.5, 3.75, and so forth. So the condition here is not the sum of the values being equal to 0, rather the total area under the graph of the equation should equal to 0. The equation in our example is y equals 1 over 60. In other words, it is a horizontal line that is going through 1 over 60 on the y-axis, as I drew in the previous slide over there. And just like every single probability in a discrete probability distribution must be greater than 0 and less than 1, with a continuous distribution, we want all the values on the y-axis to be positive. In other words, you cannot have a negative value for a density function. So the y-axis must just start at 0 and it can go on all the way up to infinity. So in our example, we cannot have a value less than 0 because that would be 10 a.m. and 60 is 11 a.m. And we know for a fact that the parcel would arrive at 10 or at 11 or any value between 0 and 60. So this parcel is not going to arrive past 11 a.m. It is not going to arrive before 10 a.m. So the probability of x being less than 0 is 0. In the sense, it is impossible. Probability x is greater than 60, but it's also 0, implying that the event x less than 0, x greater than 60 are impossible. So, how do we find this probability? The probability is simply the area under the graph of the density function over an interval. So let's take the simple example that we had. So let's say we want to know the probability that packet arrives at 10 a.m. or at 11 a.m. or any time between 10 a.m. Even before we started the problem, we actually knew or we had an event arrive at 10 a.m. or at 11 a.m. or any time between 10 a.m. and 11 a.m. This is a given fact. In other words, this is a certain event. It is bound to happen. So how do we find that probability given this distribution? It's quite straightforward, which is why we started with a uniform probability distribution, because it is easier to understand. We want the probability x's between 0 and 60, including 0 and including 60. So from here all the way up to there. So the area under the line, the black line, which is our function, is going to be the probability. So that area is simply the area under the curve, which in our case is simply the area of the rectangle. So how do we find the area of the rectangle? We know the length here is 60 and the width there is 1 over 60. So we multiply 60 by 1 over 60, which is the area of the rectangle. So that would give us 1. So what we knew at the very beginning, just by thinking about it logically, has been verified using the definition of probability for a continuous distribution, which simply is the area under the graph of the density function. In our example, that density function is y equals 1 over 60 for x between 0 and 60. And that is the simple uniform distribution. So, as an example here, the probability of choosing a time between 15 and 30 minutes after an hour is the area under the uniform density function. So just like what we did last time, here, if we want to find the probability that x is between 15 and 30, including those extreme values, all we have to do is find the length and the width and multiply them together. So the length here is 15, the width here is 1 over 60, which would give us 15 over 60, which is 1/4, we get 0.25. As an exercise, let's say we want to find the probability that x is greater than or equal to 30, which would simply mean we want to find the area over here so the length is 30, 60 minus 30 is 30, and the width is still 1 over 60. So we get 1/2. In other words, the probability is 0.5. It is easy with a uniform probability distribution because the density is simply a line, and finding the area under this line is easy because what we have is a rectangle, and finding areas of the rectangle is they are pretty straightforward, as we saw earlier. But if we have a normal distribution, it doesn't have a simple curve. Rather, it has a bell-shaped curve, the line in red. And it doesn't have an easy equation. So the density lot over there. So you look at that expression and go back and we look at the simple expression here, which is y equals 1 over 60. Clearly, that equation, y equals 1 over 60, is extremely simple compared to this monstrosity over here. So evaluating probabilities with normal distribution is not as straightforward as it is with uniform distributions. So here the Greek letters that we see, mu and sigma, are simply the mean. It's pronounced as mu. And standard deviation, pronounced as sigma. And the mean is right in the middle, which is right here, so 100, that would be mu. So as we saw in the previous slide, if the data that we have, so as you may recall, you have data, you convert data to group data, which is a frequency distribution. And you use that to obtain a histogram. From that you obtain relative frequency distribution. And using which we get a density. And if that density if it is bell-shaped, then the distribution is normal. Bell-shaped is synonymous with the distribution being symmetric. So there is something that we need to know about the mu and sigma of a bell curve. So if you look at the two curves here, one in purple, the other is in blue. Now, one of them has a mean of 0, the other has a mean of 3, but both of them have the same standard deviation. So if the mean changes, so if the mean mu changes, the density will shift either to the left or the right from the current position, depending on the change. So here, mu was 0 and it became 3. So the original mean got shifted and moved over to 3. So the entire curve got shifted. On the other hand, if the mean is the same, but the standard deviation changes, then the curve will shrink or stretch along the x-axis. So if sigma keeps on increasing, the stretch of the curve is going to stretch more and more and more. But if sigma keeps decreasing, the curve would shrink, which is why when sigma is 1, we have that curve right here. And when sigma is 2, we have this curve. Clearly, the one in blue is more spread out or stretched compared to the one in purple. it's not purple actually, it's more like magenta or pink. So what does it imply in practice? So large value of standard deviation would imply more variability in data. So if you look at the one in pink, it has a standard deviation of 1, and the data simply varies between -2 and +2, or somewhere from -4 right there to +4 to be precise. But on the other hand, if the standard deviation is 2, the curve spreads from -6 all the way up to +6. It has a greater spread. So if the standard deviation increases for a constant mean, then the spread of the data is going to increase. In other words, the variability will increase. Some interesting properties of a normal density curve. It is symmetric about the mean. In other words, the mean is going to be right in the middle. The graph has to be symmetric. The way I drew it, obviously it is not. But theoretically speaking, the left-hand side and the right-hand side of the mean must be symmetrical. So the mode is the most frequent observation, and clearly it corresponds to that point. So on the x-axis, so the x value that corresponds to the peak is mu itself. So mean would equal mode. And if you recall, the area under the curve is the probability. And from earlier, area under the entire density curve is 100%. If that is the case, then the area to the right of the mean must be the same as the area to the left of the mean. In other words, that area has to be 50%, and that area has to be 50%. If the area below a number is 50%, in other words, the probability below a number is 50%, then that number is the median. So, or 50th percentile. So for a bell-shaped curve, the mean, the median, and the mode are one and the same. So, as I mentioned, the area under the entire curve must be 1, and the area to the right of the mean and to the left of the mean must be the same, so it is 50% on either side. This is simply a refresher on the empirical rule. We know that if we go one standard deviation on either side of the mean, we have 68% of the data. If we move two standard deviations on either side of the mean, we have 95% of the data. And 3 standard deviations from the mean, we would have 99.7%. So, since 50% is below and 50 is above, meaning, so that would be 250, and 50 plus 34% would be 284, and 284 plus 13.5%, so 97.5%, 97.5% plus the 2.35, that is 94.4. furthermore by 13.5%. So it comes to P 2.5. And lastly, from P 2.5, we decrease a bit more and we end up at 0.15 because that tiny bit that we decreased by in area is 2.35%. As you can see, this area is 2.35%, and I'm adding 13.5% to that, and then I'm adding another 34%. If we add all the numbers, we would get 50% below the mean, which is also the mode and the median. So the data on the next slide represents the heights in inches of a random sample of 52-year-old males. So we want to draw a histogram using a lower class limit of the first class equal to 31.5 and class width of 1. And the second question is, do you think that the variable height of 2-year-old males is normally distributed? So we have a bunch of data points here. Those data points are raw data. And the problem says draw a histogram of the data using a lower class limit of the first class equal to 31.5 and a class width of 1. All we are trying to do is we are starting at 31.5 and adding 1, 32.5. That would be the first class. 32.5 to 33.5. That'll be the second class. 33.5 to 34.5, the third class, and so on. The corresponding frequencies are the values we count. So between 31.5 and 32.5, let's see, how many observations do we have? We don't see a lot. So that happens to be 0. 32.5 and 33.5, I have 1 over there. There is actually 31.5. So that has to be 1. So 32.5 and 33.5, we have 33.4, 33.2, 33, 33.5, and so on. So we have 4 of those, and we start filling the frequencies, and we can put the frequency on the y-axis, the classes on the x-axis, and create this histogram that we have. The y-axis is the percent, and this is the first class, the second class, and so on. The y-axis, which is in percent, is merely the relative frequency. Now looking at the histogram, if we connect the midpoints, we kind of see a bell-shaped curve. So is the data normally distributed? Indeed it is. So the height of males, which is on the x-axis, has a normal distribution, which is given by that solid line that I drew. So we want to find ahead, the area of the rectangle corresponding to a height between 34.5 and 35.5 inches, which are 2 points on the x-axis. So we have 34.5 here and 35.5 there, and the width between them is 1, so 1 centimeters, and the height over here is 0.2. That is the height of the bar. So if we want to find the area, we are simply finding the area of that rectangle, and the area of the rectangle is simply 0.2 times 1, which would be 0.2. In other words, the probability that a 2-year-old, which is our x-axis, which is what the data corresponds to, so what we have here, 2-year-old males, and what we have measured is their heights. So the probability that a 2-year-old is between 34.5 and 35.5 centimeters is 0.2. In other words, 20%. So, key thing to note here is to find probabilities under a continuous distribution or in a continuous distribution, we have to find the area under the density curve. Here, what we have in green is the area that is under the red curve, which is the normal density curve. So how do we interpret it? The way we interpret the area, the formal way is to write it as the probability that a randomly selected individual from the population will have the characteristic described by the interval of values. It's exactly what I did in the previous part. I said the probability that a 2-year-old male, which would be the randomly selected individual in this highlighted part from the population, will have the characteristic described by the interval of values. The characteristic being the height is between 34.5 and 35.5 centimeters. I should probably say that a 2-year-old male is between 34.5 and 35.5 centimeters tall. So that will be it. So here's an example on normal distributions. The weights of giraffes are approximately normally distributed with mean 2,200 pounds and standard deviation of 200 pounds. We have to draw a normal curve with the parameters given. The parameters are mean 2,200 pounds, standard deviation 200 pounds. Notice that both the mean and the standard deviation have the same units, pounds and pounds. And part B, we have to shade the area under the normal curve to the left of 2,100. And lastly, the area under the normal curve to the left of 2,100 is 0.3085. I want you to provide two interpretations, and I'm going to stick to the formal one. So let's start drawing the normal curve. The mean is right in the middle, and that mean is 2,100, and the standard deviation is £200. And what is the x-axis? The x-axis is the weight of giraffes. Next, we are going to draw the same curve. It's poorly drawn, very poorly drawn. So the mean here is 2,100, and we want to shade the area to the left of 2,100. I'm sorry, the mean is actually 2,200. And now, the value of x, the x-axis is once again the weight of giraffe. And this time we have $2,100 right over there. So the area under that would be all of that shaded part. So it is given that the area under the curve, in other words, the shaded area that we have is 0.3085. So that area, which is shaded, and we would want to interpret that. So what that value of 0.3085 means is the probability that a randomly selected giraffe would weigh at most 2,100 pounds, i.e. 2,100 pounds or less is 0.3085. Comparing to the definition here in red, so the probability that a randomly selected individual from the population will have the characteristic described by the interval of values. So the randomly selected individual here would be the randomly selected giraffe. And the characteristic is simply the weight of at most 2,100 pounds. And how do we come to this conclusion? This is relative to all giraffes, in other words, the entire population of giraffes. So in this section, our goal is to find and interpret the area under a normal curve and find the value of a normal random variable, which is the percentile. So there are two ways to find the area under the curve, in other words, the probability. One is after we standardize the data point and convert the data point to a z-score. So this value right here, z, is the z-score. And this formula standardizes the observation x. So if we start with x, which is the sample, and if it had a bell shape and some mean mu and standard deviation sigma, and if we take that sample and standardize every observation using the formula that's right here, x minus mu over sigma, then what we end up getting is a sample of z-scores. And it is guaranteed to have the same bell shape, but the mean is no longer mu. The mean is 0 and the standard deviation is 1. So we go from a normal distribution with mean with mean mu and standard deviation sigma to a normal distribution with mean 0 and standard deviation 1. Since this version right here came via standardizing every observation, the distribution of z is what we call a standard normal distribution. A standard normal distribution will always have mean 0 and standard deviation 1, and it will have a bell shape. So a standard normal curve, obviously the x-axis will change to z-scores, hence the letter z here, and the mean is 0 and the standard deviation is 1, so this would be mu plus sigma and mu minus sigma. And just like we found the probabilities between 2 points in a normal curve, we could also find probabilities using the standard normal curve. Both of them would give you the same exact answer. And I'll show you an example on both. So here is the first example. IQ scores can be modeled by a normal distribution with mean 0 and standard deviation 15. An individual whose IQ score is 120 is 1.33 standard deviations from the mean. What is the z-score? So a z-score measures the number of standard deviations an observation is away from the mean. So in our case, 120 is 1.33 standard deviations above the mean, which would simply imply that the z-score is 1.33. So we use the same problem and we want to find the probability. Let's say we want to find the probability that the IQ score is between 50 and 85. So whether we have a less than sign or a less than or equal to sign, the answer will be the same because an exact probability is always 0 with normal distribution. So let me make a note of that. In the sense that probability 50 less than x less than 85 is the same as 50 less than or equal to x less than or equal to 85. So the answer isn't going to change. So we want to find the probability between 50 and 85. So let's just have the mean here, which is 100. And we want to add one standard deviation, which is 115, 2, 130, and 145. Here, subtract, we have 85, 70, and 55. So I have added one standard deviation, I have subtracted one standard deviation, and 2 standard deviations, 3 standard deviations, and so forth. So how do we find it? We can find this directly using the calculator. The calculator, the function we are going to use is normal CDF, which stands for normal cumulative distribution function. So in your calculator, let's try this again. Seems to give me issues at times, so I may have to close and open it again. Okay. Let's close this and try opening it again. Let's try this. Okay, we'll try it anew. Finally. This is an issue with Safari, I believe. So, in your calculator, press second vars, and option number 2 is normal CDF, so 2. And the syntax here is start, end, mean, and standard deviation. Or if you have the newer versions of the calculator, it would probably say lower, upper, mean, and standard deviation. I believe in the recent versions of the calculator, you will see lower, upper, I think it is mu and sigma, so you would just enter values there and hit calculate or paste. Varies from version to version. So I'm going to type the starting point of the area. Here it starts at 50, so 50 all the way up to 85. So I need that area right there. So I'm going to start at 50, end at 85. The mean is given in the problem, which is 100, and the standard deviation is 15. Close paren, enter. The answer is 0.1582. And keep in mind that I did not use the z-score. I directly used the data values, in other words, the x values. Now, let's use the z-score approach. The z-score approach is extra work, and you don't have to do it with the availability of calculators these days. But if you insist, you're welcome to do it, but it is not necessary. As I showed you here, the calculator can do it directly for you. But if we have to do it using the z-score approach, the z-score corresponding to 50 is x minus mu over sigma, which is 50 minus 100 divided by 15, which will give us negative 50 over 15. So the z-score corresponding to 50 is negative 50 over 15. Likewise, we don't even have to plug in the x value for the next one, because 85 is one standard deviation below the mean. Regardless, if we plug it in, we have 85 minus 100 divided by 15. We'll have negative 15 over 15. We get 1. So the z-score, negative 1. So the z-score corresponding to 85 is negative 1. So we can do this in the calculator also. So we simply do second vars, number 2, starting value, the z-score, negative 50 over 15. The ending value is negative 1. Close paren, enter, we get the same answer. So whether you do it without the z-score, with the z-score, the answer will be the same. This is just extra work. You may wonder, why do we have to do this? Why do people do or find z-scores? There are theoretical reasons for that. In the past, when we did not have technology, people relied on tables, and those tables had approximate probabilities for z-scores. So people convert the data points to a z-score, then find the probability. These days, we have a calculator, so we don't have to do all that work, and I've shown it to you here in the So you might have noticed that I did not specify the mean and the standard deviation with normal CDF when I used z-scores. With z-scores, in the calculator, by default, the normal CDF assumes a mean of 0 and standard deviation of 1. So we don't have to specify 0 and 1. So here we have a z-score of negative 2.94 and a z-score of negative 1.02, and we'd like to find that area. So go back to the calculator. Second bars, option 2. The starting point of the area is negative 2.94. The ending point is negative 1.02. I don't have to specify the mean and the standard deviation because by default, with z-scores, the mean is 0, standard deviation is 1. Hit enter. So the area is 0.1522. So that is the probability between negative 2.94 less than x and less than negative 1.02. But in the question, it actually wants to find the probability of negative 1.02 less than x less than 2.94. So that question corresponds to that. So we start at negative 1.02, we go all the way up to 2.94. So that area, and that area is the area between z equals minus 1.02 and z equals 2.94. So press second vase. Now, just by looking at that picture, the shaded area in yellow is bigger than the shaded area in red. So the answer that we are going to get now definitely will be larger than 0.1522. Let's see if we have a probability greater than 0.1522. So we start at negative 1.02 and end at 2.94. We don't have to specify the mean. We don't have to specify the standard deviation. So enter. We end up getting 0.84449. So approximately it's 0.8445. Certainly, this value is bigger than the previous answer. So 0.1522, this is the area in red. And that answer is right here, area in yellow. So I think that should be a good stopping point for this video, and we will pick it up from here next time.